Hello, my name is Lalita Diaram, and this is Physics 2212 Lab 5, which is about magnetic molasses. So, for the introduction, this lab aims to model how electric fields and ring currents can interfere with the magnetic and gravitational fields, specifically with a small bar magnet. The key ideas at play are Faraday's law and Lenz's law. So to summarize the results, the time spent for the magnet to fall through the tube varied from the cardboard tube to the aluminum tube depending on the resistivity of the material and the conducting power, and that's due to the electric field interfering with the force of gravity. So for the experiment, these are the steps that we used. So these are some of the experiments we had. So this was with the magnets north facing down, and we have another test of the same thing.
Go.
And as you can see, they both fell slowly, whereas the cardboard tube fell more quickly.
Go.
Because it feels weird.
And you can see the timestamp.
And you put it like right above.
We also tried putting the south side down, so the previous one was north side down, and we tested it as well, and it fell slower than the cardboard tube, but still faster than the north side was down. So that was interesting to see. So now onto the simulation. You can see in the glow script code that we have the constants here. We also have the resistivity of aluminum along with 3 other materials that I threw in just for fun to see how that might affect the simulation. So as you can see, the constants are up there, and going through the code, you can see the geometry of the tube is taken into consideration, as well as magnetic dipole moment, which was found in the previous lab. So you can check this channel for the video on that. So going through this code, you can see there are formulas for the magnetic flux, and there's also a calculation of the force, including the magnetic force and gravitational force to find the net force. Running the simulation using the resistivity of aluminum, we can find that the time it takes to hit the bottom is around 1.675 or 677 seconds, which is about the same as the 1.8 that we found in our experiment. Now, trying out some of the other resistivities of copper, it takes a lot longer for the magnet to fall through, and this makes sense because copper has a lower resistivity and is a better conductor compared to aluminum. Now, trying out the iron, this is the most interesting given that iron has a magnetic force that it applies as well. It's shown as though it's falling quickly in the simulation, but we know that that's not true because the force also has an impact. And because of the magnetic force, we know the magnet would probably stick to the iron tube and never fall through. For the PVC, it also errs, and this is likely because the formula that we're using isn't really built to have a very high resistivity input like the PVC has. So what if R is equal to 0? I decided to test this out in the code as well. So trying out just straight up R equals 0, it errors completely, doesn't work at all, which makes sense because dividing by 0 resistivity will result in an error. So I instead changed it to 10 to the negative 30, which is a very small number. And as you can see in the graph, it seems to levitate. It doesn't fall through at all. So the observations, when the magnetic north of the magnet was down, it took slightly longer to fall through compared to when the north side was up. So obviously we weren't able to test this in the simulation, but we did get to see that in the experiment. The magnet took nearly 2 to 3 times longer to fall through the aluminum tube compared to the cardboard tube, and this is corroborated by our simulation. We could feel the magnet brushing up on the inside of the aluminum tube, which made us hypothesize that it was temporarily polarized by the magnet, causing some sort of attraction. So the analysis. The electric field and magnetic field both have direction, and the fields behave similarly enough to be able to affect and interfere with one another and cause a change in the force. The force generated by the electromagnetic field can be enough to slow the pull of gravity for small objects, such as our bar magnet. So some of the assumptions that we made is that cardboard has infinite resistivity and that human error is not significantly affecting the time data. This might be wrong because nothing can really have infinite resistivity, but cardboard does not have the electrons that can be polarized to create a field as a conductor would, so it can be assumed to be a near-perfect insulator. Dropping the magnet from a slightly higher or lower place also might affect the results by up to tenths of seconds, as mentioned earlier. So the questions, what if the resistivity was reduced to 0, and what if holes or slots were cut into the tube, how would that affect the ring currents? The answers are, as seen as in the second simulation, if resistivity is close to 0, it seems like the magnet would never fall through the tube and just levitate within it. Now I thought this was wrong at first, so I decided to do some research, but it turns out it is true. A resistivity equals 0 material would be a superconductor, which leads to interesting effects like the Meissner effect, which would result in levitation, because there would be no the magnetic field would be completely cancelled. Now, for the other question, the ring currents would be less continuous and may interfere with one another, causing a smaller damping force, and that would result in the magnet falling faster. So you might have seen Mr. Michael from Vsauce, a little cameo on the title page. If you're wondering where I got that picture from, it's from his video on Lenz's law. So if you want to go check that out, it'll be linked in the description. I thought it was really fun to watch. Thank you, and peace out.